Okay, so last lecture we had finished off quite abruptly with Newton's laws of gravity, and we didn't quite finish that, but I think I'm going to ask the GSIs to expand on that discussion a little bit in their sections, because I really want to spend today focused on special relativity. And you can see I don't have any demos today. It's a couple of lectures that you can't demo very well in a class like this, and relativity is one of them. So this is going to be a Blackboard talk today, unfortunately, but hopefully it'll still be pretty interesting. So today we're going to spend all day talking about Einstein's theory of special relativity. Right? And to do that, first we have to give a little context in terms of what came before that. And what came before that was classical relativity. And we're going to define this. So, but we've already been talking about this quite extensively in the class, so we just did not give it an official definition. So we've already seen this throughout Newton's three laws. Okay, and let's explain what classical relativity is, or what it assumes. So, the actual statement of classical relativity, let's write it down. It says the laws of physics are the same in any non-accelerating frame of reference. So we've already talked about inertial frames of reference, and we've seen examples of moving between different frames of references. So, being an observer on a train, or observer on the ground, or observer in a rocket ship, an elevator. So we've had a lot of discussions about frames of reference and relative frames of reference. Okay? The principle of classical relativity is that the laws of physics are the same in any non-accelerating frame of reference. Or let me put this in parentheses here, because we often refer to non-accelerating frame of reference as an inertial frame of reference. So any non-accelerating frame of reference. Okay, so let's talk a second about what we mean by the laws of physics. So far we have seen Newton's three laws, and we've seen them in multiple ways. So these are all laws of physics. And the classical principle of relativity would claim that those three laws hold in any frame of reference as long as it's not accelerating. So the laws were that the first one, an object in motion stays in motion with constant speed. An object at rest stays at rest. So that holds in any frame of reference, whether that frame of reference is moving or it's at rest. So a passenger on a train moving at constant velocity sees an object in front of them at rest. That's moving with a constant velocity. It's just zero. The observer on the ground sees that moving at a constant velocity as well, just it's the velocity of the train. Okay, so the law holds in any non-accelerating frame reference. Second, force equals mass times acceleration. Okay? You do not get an object accelerating unless there is a force acting on it. Okay? If there is a force acting on it, you see the acceleration in any frame of reference. And the third, action-reaction for any force is equal and opposite force. Okay? That holds independent of whether you're in that moving frame of reference in the train or you're in the stationary frame of reference on the ground. Okay? We've expressed those in other ways: conservation of momentum, conservation of energy. Those are all laws of physics, and they hold independently of what your frame of reference is, whether it's moving or stationary. Okay, so that is the classical principle of relativity, and it seems to hold pretty well, okay, at least in our everyday experience around us. But there are two assumptions that we actually make when we are talking about this classical principle of relativity, and they were assumptions that Newton and Galileo built into the formulation of the laws of physics, but it turns out that they are absolutely wrong. They work pretty well in the world around us, but they were wrong, right? And, Newton and Galileo are pretty smart people, so it's not obvious that, it shouldn't have been obvious that these assumptions were actually wrong, but they turn out to be. So let's write down what those two assumptions are. Okay, so there are two wrong assumptions that went into that formulation. So the first one, which turns out to be wrong, is that velocities add linearly when comparing two frames of references. Okay, so what do we mean by that? Well, we've already seen this, okay, and we've been using this a lot, okay? And it turns out to be wrong, okay? But for typical speeds in the world around us, it's a pretty good approximation, so that's why we still use it. Okay, so velocities add linearly when comparing two frames of reference. So let's look at two frames of reference. Here is us riding on a train, okay? So this is the train frame of reference, okay? And let's say in this frame of reference, we're going to throw a ball, okay? And it's got some velocity off to the right, okay? In the train's frame of reference, this is the velocity of the ball, okay? Whatever we just find there, okay? Now, the assumption from classical relativity is let's look at a second frame of reference. Let's look at the ground frame of reference. Okay, so in this frame of reference, here is our passenger. There is the ball that the passenger is throwing. Okay, here is the ground, and now we are an observer standing here at rest in the ground, and we're watching that train go by. Okay? So in this frame of reference, that train has some velocity. Let's give it a velocity off to the right, so it's moving off to the right. Okay? And in classical relativity, we would say that this ball is also moving off to the right, but its speed is just the sum of the ball and the train, okay? So in this ground frame of reference, okay, the ball moves off to the right with the combination of the speeds of the train and the ball, okay? Pretty safe assumption if you think about the world around us and how it looks, okay? And so, so Newton and Galileo built this assumption into classical relativity, okay? But it turns out to be absolutely wrong. This is how speeds add when we're at very slow speeds, so slow compared to the speed of light. But there are major modifications to this when you get things going faster and faster. Okay? And we'll be talking about that in more detail. Okay, but this is an assumption that is built into classical relativity, and it's a wrong assumption. So now the second one, which is even, I put that on the wrong board. Let's leave that up there. Okay, the second assumption, which is even more fundamental, is the one that really seems like an obvious truth, but is absolutely wrong. And that is that time is absolute. And it's completely independent of your frame of reference. This one is such an inherent assumption that it's even hard to pick out where in classical relativity that comes to play, but it comes into play everywhere. Everywhere where you're talking about measuring the speed of objects, the acceleration of objects. You're talking about measuring distances over amounts of time, and the inherent assumption that Galileo and Newton both made, which everybody else made up until Einstein came along and corrected us, was that time, the measurement of time, was completely independent of what your frame of reference was. So the observer on the ground and the observer on the train were reading the same exact times on their watches at all times. Okay? This is, turns out to be wrong. And it turns out to be the biggest stumbling block for understanding special relativity. So let me tell you, let me stress to you that everything becomes a lot easier in studying relativity if you give up this assumption completely. Okay? And what you need to think about is that every frame of reference has its own clock. Okay, we'll explain how that comes in just a few minutes. Okay? But as long as you can keep that in mind, everything else we're going to say in the rest of this lecture will make a lot more sense. Okay? The time you measure when you look at your watch is the time in your frame of reference. Okay? And that is not the same as in somebody in a different frame of reference. Right now, you guys are all sitting in this room together. You're all at rest, more or less, except for the guy who came in late. Now he's at rest. Good. Okay, now you're all in the same frame of reference. You're all measuring time the same as all your neighbors. Okay? But when you get up and start walking away, you're entering a different frame of reference, and time is passing differently for you than it is for your neighbors who are still in this frame of reference. Okay? Time is fixed to your frame of reference, and you always measure time in your frame of reference. Okay? Everything we're going to say from here on out is trivial if you keep that in mind. Maybe not trivial, but it's a lot easier to understand. Okay, relativity. Special relativity comes from studying the speed of light. Okay? And let me write down the speed of light and what it is. Okay, the speed of light. This has been known since the late 1600s. Okay? People before that time knew that light traveled really fast. Okay? They couldn't measure how fast it was going. So it wasn't until a while after Newton came up with his three laws that people could measure the speed of light, and they ended up measuring it very quickly by looking at the orbits of moons around Jupiter. Using Newton's laws, you can predict the orbits very carefully. Okay? And then they could see when Jupiter was on the other side of the solar system from us, they could see that when they were watching the moon's orbit, that they were delayed where they should be. And then somebody realized, hey, they're delayed because light's taking a finite amount of time to reach us from Jupiter. So that is the light travel time. And that's how they figured out the speed of light about 400 years ago. So the speed of light, let's write it down. We're going to call this C. It's such a fundamental quantity. It's got its own letter. C is the speed of light. It's 3 times 10 to the 8 meters per second, which is 300,000 kilometers per second. Okay? And if you think in terms of miles, that is 186,000 miles per second. Okay, so fast. Speed of light is very fast. Okay, so the background that led up to Einstein's theory of special relativity comes in large part out of the study of electricity and magnetism. So we haven't studied electricity yet, nor magnetism yet. We will get to that in later next month. Okay? But historically, the study of electricity and magnetism, even though it continues today, it really peaked in the late 1800s. Okay. And it peaked with the unification of these, which we'll talk about later. But it peaked with something called Maxwell's equations, which I am not going to write down. Okay. But the key about Maxwell's equations is that when they were studying electricity and magnetism, is that Maxwell's equations predicted light. So until that point, there was a lot of debate about what light actually was. It wasn't absolutely clear. Through the study of electricity and magnetism, basically Maxwell and his colleagues developed a theory that explained what light is and how fast it moves, and it made an incredibly interesting prediction, or incredibly odd prediction. Maxwell's equations predicted that that the speed of light is constant for any frame of reference. Okay, let's let that sink in for a second. So that is completely against classical relativity. So what they were predicting is if you replace this ball here with a beam of light, that the passenger on the train would be measuring that beam of light traveling at this speed, which the theory predicted exactly, 186,000 miles per second. But then if you change your frame of reference and to this ground observer and you redo all the calculations and you look at what the speed the light is traveling with, then you get the exact same answer, that this observer sees light traveling at 186,000 miles per second, independent of the fact that the light is being emitted on the train, which is moving off to the right. Okay. Very odd prediction. Completely went against all of classical relativity, and so most people assumed that it was wrong, that there was something wrong with the laws of electricity and magnetism, and that this was just some odd little quirk about the theory. We've already talked earlier about how physical theories should be thought about as models, and they're models of how something works around us. And whether they're right or wrong depends on whether they explain observations or not, right? And whether they're useful. And so most physicists thought by the late 1800s that these equations of electricity and magnetism were useful, but they must be wrong because they made this, at some level, because they made this odd prediction about the speed of light, and that somehow that would get resolved later on. Okay? So the common notion that most physicists held at that point was that this prediction was actually a statement that there was some special frame of reference in the universe. Okay? We've talked about lots of different frames of reference, but when you think about it, we've got the person on the train's frame of reference, we've got the ground's frame of reference, but that's on the Earth, which is orbiting the sun. So maybe we want to look at the universe from the sun's frame of reference, but the sun's orbiting the galaxy, so maybe we want to look at the laws of physics from the galaxy's frame of reference. But the galaxy is moving relative to other galaxies. So what is the basic frame of reference? Classical relativity would have claimed that there is no special frame of reference. You could look at the universe through any of those and you get the same answer. But this suggested that maybe there was a frame of reference, the special frame of reference that you've heard called the ether, which was fundamentally the frame of reference for the universe. Okay? Now, there was a very famous experiment called the Michelson-Morley experiment, which you may have heard of, which basically was designed to prove this prediction wrong. Okay? Michelson-Morley built an experiment that they wanted to show that the speed of light was basically dependent on your frame of reference. And they built an experiment designed to prove that. Okay, so they built this experiment around the 1880s. Well, they ran this experiment during the 1880s. And let me tell you a little bit what the experiment is. So they basically built a very sensitive device that was designed to measure small changes in the speed of light. Okay? It's really difficult to actually measure the speed of light by itself, because it travels so fast, okay? So you can do it in a very short time. But the technique they developed was extremely sensitive, not to the overall speed of light, but to little changes in the speed of light. So they were very sensitive to being able to measure if the speed of light had changed by a tiny amount. Okay, so they knew that the Earth was, their experiment was in the Earth's frame of reference, and the Earth was orbiting around the sun. So they made a device that was supposed to measure the change in the speed of light as the Earth orbits the sun. So let me draw. Here's the sun. Here's the Earth at different points in its orbit around the sun. And the Earth, of course, is changing its direction, its velocity as it orbits over the year. Okay? And the orbital velocity of the Earth is about 30 kilometers per second. If you compare that to the speed of light, which is 300,000 kilometers per second, then this is about 1/10,000th of c. So they predicted that if they were measuring the speed of light in this direction, right, when the Earth was going in this direction, compared to in this direction, and then finally compared to in this direction, right, that they would see a change on the order of 1 to 2 parts per 10,000 in the speed of light. Okay? Just because if there really was this ether frame where light was traveling at the speed of light, then when they were measuring it from the Earth, which had to be moving through that because the Earth is not a stationary frame of reference, then they would see this shift in the speed of light. Okay? And the instrument they designed was extremely sensitive. Even though this seems like a small number, it could have easily picked that up. Over the course of 1 year and then several years, they saw no change. They saw no change in the speed of light, independent of which direction the Earth was moving, which is not at all what they expected. So they absolutely expected building this that they would see that this prediction of electricity and magnetism was wrong, that the speed of light actually varied depending on the frame of reference. Okay, so what this experiment proved, though that wasn't its intention, was that this prediction was absolutely correct, that the speed of light is constant, independent of your frame of reference. Anybody in any frame of reference, as long as it's not accelerating, will measure light traveling with the exact same speed as anybody in any other frame, which completely goes against our classical relativity. Okay, so By 1905, which is the year that Einstein came up with the special theory of relativity, so that was, that was 2 decades after Michelson-Morley experiment had happened. At that point, most physicists actually just thought there was something wrong. There was something wrong with that experiment, or there was something wrong with E&M, but nobody or very few people actually questioned whether there was anything wrong with classical relativity, because it just seems like such an obvious assumptions that were made, that went into it. Okay? Einstein was different. He was radical. And he realized that the only inconsistency between this prediction and what people expected the outcome of this experiment to be was based on the assumptions that Newton and Galileo had made 300 years earlier and more in classical relativity. So Einstein, basically overnight, came up with his own relativity. Instead of classical relativity, it is special relativity. And he also made a couple of basic assumptions that went into special relativity, but these were very different from the assumptions that Newton and Galileo made. So, special relativity. Okay, the assumptions are, the scientific word for an assumption is a postulate. Okay? He made postulates, and those postulates, of course, had to be proven or disproven. Right? But his postulates on the law that went into the law of special relativity, there were 2 of them. The first is the exact same postulate that was made for classical relativity, and that is that the laws of physics are the same in any non-accelerating frame of reference. Okay, let's talk about this one for a second. So this is the exact statement we made for the classical relativity, but let's put this back in historical context, right? Because at this point, the majority of physicists were interpreting this electromagnetism result, this prediction that speed of light was independent of the frame of reference. Most physicists were interpreting that prediction as somehow telling us that there actually was a special frame of reference. There was something, and there was this ether frame of reference where the speed of light was constant, and that we just weren't very good yet at discovering where that was. So Einstein's first postulate, the laws of physics are the same in any non-accelerating frame of reference, is basically saying, if you read between the lines, that no, there is no ether frame of reference. Any frame of reference is equivalent to any other frame of reference, and laws of physics are the same in all of them. The second postulate that went into special relativity is that the speed of light is a constant, is a law of physics. Okay, so his assumption is that, his postulates are the laws of physics hold in every frame of reference, and that the speed of light being a constant is one of those laws of physics. So they had to hold in every frame of reference. Okay? That the speed of light you measure does not depend on your frame of reference. Okay, those are the 2 postulates that went into his theory, and these 2 postulates turns out they can only hold if we give up that notion that time is measured independently of your frame of reference. Okay? And let's derive that, why that is true. And we're going to do that really easily just by looking at this example again, where we've got an observer on a train, observer on the ground, but instead of throwing a ball, we're going to have this observer shine a flashlight. Okay, we're going to look at the speed of the light coming out of it in the two frames of reference and see how that affects time as measured by those two observers. Okay, so let's set up our experiment. Let's see, I'm going to need a couple boards for this, so let me... Okay, so let's start out with the observer on the train. Okay, so we're going to start out in the train frame of reference. Okay, so we've got the observer, and the observer is going to shine a flashlight, and we're going to do a really simple experiment here. So here is our observer in the train. Okay. In this frame of reference, the observer is at rest, and this observer is just going to take a flashlight down here on the ground. That's a really bad flashlight, but okay, that's a flashlight shining upwards. And all that observer is going to do is to shine that light upwards, let it bounce off of a mirror at the top. So there's the light shining upwards. It's going to come back down to the ground. Okay? And all we want is for that observer to measure the amount of time it takes light to go up to the top and back down. Okay? So let's give this a distance here. This is a distance d. Okay. And let's just look at the amount of time it takes. So the light is traveling at the speed of light, c. So it's traveling up with the speed of light and downwards with the speed of light. Okay. Einstein tells us that that speed of light is the same in any frame of reference, so that's just a constant. It's 186,000 miles per second. Okay. And so the total distance traveled by that light is 2 times the height. Okay, so the separation between those mirrors, so 2d. Okay, and the amount of time so for the amount of time for the light to bounce off that mirror and return, so the amount of time is just going to be equal to the distance divided by the speed of light. Okay? So remember, speed is distance over time, so you can turn that around and say the amount of time it takes for that light to travel is the total distance, which is twice the height, so it's going up and returning, bouncing back, divided by the speed that it's traveling at. Okay? Let's give this a special little symbol here. Let's call this T naught. And let's remember that T naught is the time of that light to travel back and forth in the train frame of reference. Okay. So that is the amount of time in the train frame of reference, so observer on the train. Now let's look at an observer on the ground. Okay, so an observer on the ground is going to see a combination of two motions, right? So the observer that is watching this from the ground is going to see the light being emitted from the bottom of the train, going up and hitting the mirror and returning down. But during that whole time, the train is moving off to the right. So the mirrors that the light is bouncing off of, okay, is traveling to the right. And so these three events, light is emitted, light is reflected, and the light returns down to the ground, okay, those are, even though they line up and down in this frame of reference, the observer on the ground is going to see all of that moving off to the right, right? So let's draw what that looks like. So here is the top of the train, and here is the ground where the light is first emitted. So here's the flashlight shining up, okay? And once again, we are an observer here on the ground watching this happen. So everything in this frame of reference is moving off to the right with some speed v. So v is going to be the velocity of the train. Okay. So we're going to look at three different points. So there is the initial time when the light has been emitted. Okay. So here is two later times. Okay. So that whole mirror and apparatus is moving off to the right. Okay. Let's just draw what it looks like. Here is when the light is emitted. Okay. So that light starts up, but in this frame of reference, it's traveling to bounce off of this mirror, which is moving to the right. So in this frame of reference, the light is moving up in this direction. Okay. And it bounces off the mirror and comes back and hits the bottom. Okay. So that is all moved to the right because the train is moving to right with that speed v. Now, let's think about the times involved here. Okay, first off, important point, this distance has not changed. That is the height of the train. So this observer on the ground is seeing that distance between those two points not changing. Okay. But this observer, according to Einstein and the laws of electricity and magnetism, sees light traveling with that same speed c along this path. Okay. The quandary is that during that time, the mirrors have moved, right? So let's imagine that there is some time that it takes in this frame of reference for the light to travel. Let's call that t. So t is the total time for the light to go up and hit that ceiling, come back. Okay. Let's look at these distances. So this distance from the initial point to the point where the light hits the top. Okay, how far has the train moved during this time? Well, it has traveled half of the amount of time, right? The total time. So the distance that it has moved is the speed that the train is moving times 1/2 the time, so v times t divided by 2. And likewise, this distance is it takes the other half of the amount of time, so distance is v times velocity times time over 2, 1/2 the time. Okay, so we have a triangle here. Okay, so what we need to figure out is how far the light has traveled during this amount of time. So the light has taken this path up and this path back. Okay, so we want to find this distance right here. Okay. Let me point out, though, that we've already violated classical relativity in this picture because we've already required that the speed of light is constant, that the light is moving at c. Okay? Classically, we would have said that the speed of light was moving at the initial speed in the train frame of reference, okay, plus the velocity that the train is giving it. Okay? But because we're trying to understand the implications of special relativity, we're forcing this to be C. That's it. That's what it is. This frame of reference, it has to be C. That's what Einstein tells us. Okay, so let's go ahead and draw this triangle again. The path of the light over here. Okay, so we've got this triangle. I ran this math by my 7th grader, so I know we can handle this. Okay, so we're going to find this triangle. We want to find the distance of this that the light has traveled here. So this bottom here is the speed times half the time. Okay, this height here is just the separation between those mirrors. So that's the height between the mirrors. And what we want to find is this length. Okay? This is just Pythagorean's theorem, which I'm not going to derive for you. But we know this is just d squared plus, it's just the sum of the squares of these two sides, and then the square root of that. So if you don't get that, ask your GSI to explain that. Okay, that's just Pythagorean's theorem. That is the length that the light has traveled from this point to this point. Okay? And so it's the same amount of length that it has to travel to get back to this point in this frame of reference. Okay? So in this frame of reference, the total distance that the light travels is going to be equal to twice this distance, because the light goes up and goes down. So it's 2 times the square root of d squared plus v squared t squared over 4. Once again, I apologize for the math, but that's okay. Conceptually, what we need to know in this picture is that this distance that the light has traveled in this frame of reference is bigger than this distance that the light has traveled. Okay? Because of the shift in the position of the mirrors that it's bouncing between. Okay, so if you don't get the math, then just know conceptually that that distance has to be larger than the distance the light has traveled in the other frame of reference. Okay, so this is the total distance. The time now for the light to return. In this frame of reference, the time is just the distance that's traveled divided by the speed of light. Just like in this frame of reference, the amount of time for it to go up and return was the total distance traveled divided by the speed of light. The same is true in this frame of reference. Okay? It's just the distance has changed because the mirrors are moving, but not the speed of light. Einstein tells us that the speed of light has not changed. So the total distance is 2 times the square root of d squared plus v squared t squared over 4 divided by c. Okay, that is the time it takes for the light to go up and bounce in this frame of reference. This actually has t on both sides, so you have to do a little algebra to solve this. Okay? And if you do that, we're not going to do that here, but we're going to talk about the implications of it. If you solve for that time, you get this interesting formula, which is in your book, that, so in the ground frame of reference, the amount of time it takes to bounce back and forth is equal to the amount of time it takes in the train frame of reference multiplied by this funny algebraic expression, 1 minus v squared over c squared, 1 over the square root of v squared over c squared. Now, if you're not following the algebra, don't worry about this too much. Okay? We call this factor the gamma factor, and it pops up everywhere in relativity. Okay? It just means that the the time measured in the frame of reference of the ground is equal to some factor times the time measured in the train. The important part here is to realize that those are not the same. Those times are not the same. And this factor, which we call the gamma factor, depends on the speed of the train, how fast it's moving. Okay? So let's just clarify this, that our symbol T here is the time for the ground observer. Okay. T naught is the time for the train observer. And they are related by this factor gamma, where gamma is always greater or equal to 1. And this is called the time dilation factor. Okay, so let's look at gamma a little bit. Okay, just how that behaves as we go faster. But let's look at the implications of this first. The time measured on the ground is always greater than the time measured on the train. So you, as an observer on the ground, always see more time passing than the observer on the train sees for the exact same event to happen. So the light goes up, it comes down. The observer on the train says, that took 2 seconds. Okay. You, on the ground, say, no, that took 4 seconds. What are you talking about? It's the difference in the frame of reference. The fact that your time is always larger on the ground than the observer in the frame of reference means that you are seeing time pass faster than the person on the frame of train, okay? Or their time is being slowed down. You always measure time passing at the same rate in your frame of reference. Okay, so let's look at gamma just a little bit. Just because this factor pops up everywhere in special relativity. So if you understand at least the basics of how it is numerically acting, you can understand some of the consequences of it. So the gamma factor. Okay, so gamma, you see this little equation over here. 1 over the square root of 1 minus the speed of the frame of reference you're looking at divided by this speed of light squared. Okay, so let's just look at the implications of this. So V over C, the speed of the train in this case, divided by the speed of light, that's really just the ratio of the frame of reference to C. So we've been talking about the train, but now you can imagine that this might be a rocket, it might be a car, it might be a planet, it might be any frame of reference that's moving with some speed v relative to your frame of reference. Okay? So let's just make a little table so we can understand a little bit how this gamma factor changes with increasing speed. Okay, so this is the ratio of the speed of the frame of reference to light. So this is how fast that train is moving past you. Okay, and let's look at the gamma factor for this. So if that train is at rest relative to you, okay, that means that you guys are both in the same frame of reference. Well, the gamma factor is equal to 1. Okay? So remember that the time observed by you is equal to the gamma factor times the time observed in the frame. So that makes sense. If that train isn't moving, it's at rest, then you're measuring the same amount of time pass as the observer on the train. Okay? So let's see how this goes as we scale up. Let's say you're moving at 10% the speed of light. Sorry, that train is moving by you at 10% the speed of light. Then the gamma factor is 1.005. Okay, so you can see why we might have missed the effects of relativity. Even if that train is moving 10% the speed of light, which is really, really fast, then if the observer on that train sees that light bounce in 1 second, you will see it happen in 1.005 seconds. So not a huge difference, even for what is a pretty high speed. Okay? So the effects really kick in when we start going faster and faster towards the speed of light. So let's put some more numbers in here. If we're going half the speed of light, 0.5, then this gets a little bit more respectable. 1.155, so we'd see about 15% difference in the amount of time between the two frames of reference. Okay. 0.99, so if that train's going by at 99% the speed of light, then the gamma factor is 2.294. Okay, now we're seeing some effects, right? That train is going by at 99% the speed of light. Then what that observer sees 1 second taking that light to bounce up and down, you see it taking about 2.3 seconds, 2.294 seconds. Okay, so pretty major effect for things that are moving close to the speed of light. Okay, let's do it. 99.99% the speed of light, 0.999. Okay, the effects are getting even bigger, 70.71. So, time is, in this frame of reference, is going by 70 times slower than in your frame of reference on the ground. Okay? And finally, let's say what happens if this is equal to 1. Okay? Well, if you look at that equation up there and you plug in 1 for V over C, then you see it's going to be 1 over 0, which means infinity. So that means what takes 1 second on that frame of reference of the train takes an infinite amount of time for us. So what that really interpretation of that is that if that train could actually go the speed of light, time would look completely stopped on that train to us, observer on the ground. Okay? So we would see that person going by and everything just completely stopped in that frame of reference. Time is going along perfectly normal for us. We don't see any effects in our frame of reference. You always measure time progressing at a normal rate in your own frame of reference. It's what you are seeing in the other frame of references that gets affected when they're moving relative to yours. Okay, the caveat to that, which leads to the potential paradoxes that people like to think about, is that the opposite is happening to the observer in the train. The observer is in the train, and they're just seeing time progress at their normal rate, and they're seeing you whipping off in the opposite direction, right, with whatever speed that train is moving with. Okay? Except for to them, it's not the train that's moving, it's the ground that's moving. So they see the exact opposite effect. They see time progressing normally in their frame of reference, but it's moving slower for you. Okay? That seems like it is an inconsistency between those, that I see time moving slower for the person in the train. The person in the train seems time moving slower for me on the ground. Okay? But it's not. And it's not inconsistent because they are in different frames of reference. Okay? They are not in the same reference. They're not measuring the same times. Okay? You only need to worry about the time passing between the two of them when they get back into the same frame of reference. Okay? So the The big example of that is what's called the twin paradox. You guys have probably heard of this before. Okay, so the twin paradox is actually not a paradox. It's just a really good physics problem. Okay, the twin paradox asks this. So you've got two twins. One's an earthbound twin, and the other one is an astronaut. Okay? So that astronaut twin is going to take a long journey. So that astronaut twin is going to travel to a neighboring star, okay? And going to turn around at that star and come back. Okay? And on the rocket ship, let's give it a number here. So let's say twin number one leaves Earth on a rocket, traveling at 90% the speed of light. Somebody just whistle about that? That's a large number, huh? Rocket. Okay, traveling at a speed equal to 0.9 times c. So 90% the speed of light. Okay, so let's imagine that twin, so here is Earth, here is neighboring star. Let's imagine that twin is going to travel out at 0.9 c, and let's say the twin sees a time t naught is equal to 10 years to reach that neighboring star. So the twin in the spaceship, okay, travels 10 years out, reaches the neighboring star, slows down, turns around, takes the measurements, whatever they're getting there, picks up all the gold maybe, I don't know, comes back to Earth. So they return with 0.9 c, and let's see, I shouldn't have called that t naught. Let's say that's just time to for number one, to travel there is 10 years, and traveling back is also 10 years. So 10 years out, 10 years back, the total amount of time that twin has traveled, according to them, is 20 years. Okay? But they've traveled at 0.9 c, right? So there's a gamma factor there. The gamma factor for 90% the speed of light. Oh, I didn't write that on there. I should have put that on there. Let's see. Oh, let's just change it. They travel out at 99% the speed of light. That makes it easy. Travel back at 99% the speed of light. Okay? So the gamma factor that they see is 2.294. I mean, that's not what they see. That's what the person on the Earth sees. So that's the gamma factor for that speed. Okay, 20 years. Now, the twin on the Earth has never changed their frame of reference. So the twin on the Earth seems a completely different time pass. So twin number two on Earth sees a time pass, which is just gamma times t naught, the twin that has traveled out to the neighboring star and back. And that is going to be equal to, so it's 2.294. That's the gamma factor. So this twin on Earth sees that gamma factor for the twin that travels out, and when the twin travels back, times 20 years, which is equal to 46 years. So that twin, number one, that traveled out on the spaceship has aged 20 years during this trip, and the twin number two that stayed on Earth aged 46 years. So they are not the same age. when that twin number 2 returns. Now, the paradox, or the proposed paradox, is that why is there a difference when the twin number 1 on the rocket ship would see twin number 2 moving backwards with the same speed, right? 99% the speed of light when twin number 1 is traveling out. Why don't they both see this time dilation? And why would one of them be any older than the other one when they return? It seems like a paradox, but it's not. And the reason is that twin number 2 has never changed their frame of reference. Time has been passing regularly for them, and they've never went from frame of reference to frame of reference. Twin number 1, however, has changed their frame of reference several times, right? They're starting in the Earth frame of reference, where their clocks are moving the same as twin number 2. They accelerate on that rocket ship, going in this direction, out to that star. They're in a completely different frame of reference. Time is progressing at a different rate for them. They get to that star, and they have to slow down and stop. When they stop at that star, they're suddenly back in the Earth's same frame of reference of the Earth, if they're rest relative to the Earth. Okay, but then they accelerate back in the opposite direction in a completely different frame of reference. Okay? So you can kind of think of it about as and then they come back and stop right at Earth. And then they're back in the Earth frame of reference. Okay? You can kind of think about it as this. As long as they are in different frames of reference, who cares? They're going to see whatever they see between the other ones. But when that twin returns back to the Earth frame of reference, they have shifted into a number of different frames of reference, and the time is what it sort of locks it in, right? It's changed because they have been changing their frame of reference during that whole time. So twin number 2, nothing's really happened. Okay? They're just progressing on at their normal speed. Okay? Twin number 1's been busy changing frame of reference continuously, and only when you switch frames of references does it really affect this progression of time between the two. Okay, so weird predictions, right? But this has, well, nobody's sent their twin out, but this prediction has actually been verified many, many times experimentally. Right? And it's actually verified every single day by satellites. So we have satellites that orbit the Earth, right? So they are moving with constant speed relative to the Earth as they orbit. So, so this is very well verified. Okay, every time a satellite, the satellites orbit the Earth, right, constantly, they're in a different frame of reference than we here on Earth are, because they're moving with a speed relative to us. And that means time is moving slower. Okay? And so for a satellite in low Earth orbit, so like the space station, okay, the clocks on, for example, on the space station that the astronauts use lose 31 microseconds each day. 31 microseconds. So that seems like it's not such a big number, 3 parts per millionth of a second. But modern clocks, even your wristwatch or the clock in your phone is much, much more accurate than that. This is trivially easy for us to measure these days, time to this precision, and it's absolutely measured every single day on satellites that are going around the Earth. So we know that these predictions of special relativity are absolutely true. So yes? So the question is if there's any adverse effect on astronauts if they go up and come back down. Only that they're probably, a few seconds younger than they would have been if they came on Earth. So, yep, no, there's not, the time effects don't have any effects on them. So the weightlessness has big effects on them, on their anatomy, so, but time-wise, there's no major effects, so, yeah. Then we can be jealous. Okay, so, oh, by the way, I was going to mention, so, in fact, I would say that's not only measured, but it's actually crucial. So GPS satellites, the ones that we use to find our positions with our iPhones and such, require on us to correct for these effects, because otherwise they would be wrong, because the time is traveling is different for them than it is in our frame of reference. So, so this is sort of a, actually I think it was a surprise for the early satellites when they figured out that, wow, time was really traveling different for them. We have to take account of special relativity to really understand their motion. Okay, big effect. Other effects of relativity. Energy. Okay, relativistic energy. So we're not going to derive this. I'm just going to tell you what we see. So here is a particle of mass m, and it is moving off with some speed v. Remember from classical physics, we would say it has a kinetic energy of 1/2 mv squared. So relativity gives us a completely different prediction. Relativity would tell us that the energy of that particle is equal to the gamma factor times its mass times the speed of light squared. Remember the gamma factor over here and how it changes. So this tells us that if we know the gamma factor and we know the mass of that particle, we can tell you what its energy is. Okay? Now, the weird thing about that is when, there's two weird cases. Let's look at them. First off, when v is equal to 0, that particle is just sitting at rest. Okay? The speed is 0, but the gamma factor is equal to 1. So the immediate odd prediction of this relativistic energy so for v equals 0, when that particle is just sitting there at rest, is that the energy of that particle is its mass times the speed of light squared. Completely came out of nowhere. Okay, nobody had ever seen anything like this before. This was Einstein, one of Einstein's predictions for the energy. And what this means was stuff just sitting there has energy just because it has mass. Okay? This is a prediction that mass is energy and energy is mass. So, and this is vice versa. Okay? So, if you start that particle moving, it will gain kinetic energy, but if it's at rest, it still has energy just because it's got mass. Okay, there are two implications of that. One is if we could actually somehow convert that mass to other forms of energy, we could use it. Okay, and it turns out to be a huge amount of energy. And this is, so mass is energy. Can we access it? Yes. In fact, we access it every day. The sun shining comes from the conversion of mass to energy. Okay. And on Earth, we can access it through nuclear reactions, okay, the creation of nuclear energy. So nuclear energy, which we will talk about later in the semester, is the direct conversion of mass into energy that we can use to convert to other forms, usually heat. Okay. Very odd prediction. Okay, let's see. Let me get another board here. Other implications. That also predicts if we add energy to a system that we will change its mass. Okay, so the example of that is if you took a pot of water or some liquid and just boiled it. So you put a little fire there. That's supposed to be a Bunsen burner, by the way. And we just heat it up. Okay, so we're adding thermal energy to the system. As the energy increases, the mass of that system increases as well. So if you heat up, so when you boil water for pasta or rice on the stove, you're adding energy to it. You're actually increasing the mass of it. Caveat to that, though, is it's way too small to measure. Okay, that's a very difficult measure to make. But we know from the other predictions that it has to be true that we're actually changing the mass of the system. Okay, the third one and the really most interesting one, probably. I don't know, equals mc squared is pretty interesting. Almost as interesting, comparably interesting, is the cosmic speed limit. Okay, and this is a prediction that nothing with a mass can travel faster than the speed of light. Okay, so as the speed of light approaches, as the velocity of an object approaches the speed of light, so that's where this is approaching 1, okay, this gamma factor goes to infinity. And if you look over here at the energy, right, the energy, which is equal to gamma times mc squared, if you're getting that particle moving towards the speed of light, gamma goes to infinity. That means that goes to infinity as well. Okay, so what this tells us physically, it takes infinite energy to accelerate a particle to the speed of light. Okay, that means it's impossible. We don't have infinite amount of energy. So there's no way we can make something get to the speed of light. Yes? Yeah, so, okay, great. So this is a news story that just came out, good timing, that at a particle physics lab in Europe, they measured particles which they think were going faster than the speed of light. So Einstein tells us that's impossible, that particles can't be accelerated faster than the speed of light. Be skeptical. What they're doing is extremely difficult measurements, but it's really interesting if it does. There is actually a caveat to this, which I want to make, which is that, which does affect this, which is that Einstein's theory predicts from this that we cannot accelerate particles to the speed of light, or faster than the speed of light. But the caveat is that it doesn't actually tell us that they can't exist. It just tells us that we can't make them exist if we can't take something that's moving slower than the speed of light and make it move faster than the speed of light. But it doesn't prohibit those from existing if they are naturally born moving faster than the speed of light. And we have a name for those. They're called tachyons. Okay? And I'll tell you what, we will spend 5 minutes at the beginning of next lecture talking about the implications of tachyons, okay, to finish up this discussion. So.